Hello viewers, this is Dr. Dheeraj Malhotra, and today we are going to discuss a data structure known as binary search tree. Up till last video we have discussed binary tree in detail. So binary search tree is an important variation of binary tree with a property that here all nodes in the left subtree have a value less than that of a root node. All nodes in the left subtree have a value less than that of root node, which means, for example, here we have 50 in the root node. So all those nodes in the left subtree, if you notice, all of these nodes are carrying values which are less than 50. At every level you can check. For example, with respect to 50, all these are smaller values. Okay, with respect to 19, 7 is smaller. With respect to 32, 25. So if you consider any node as a root, okay, then the left subtree must be consisting of values lesser than that. This is a property of binary search tree. And another property is that all nodes in the right subtree have a value more than that of root node. Okay, this is just opposite of left subtree property. So all nodes in the right subtree with respect to root, for example, if we consider this as a root, then all these values, all these four values are greater than 50. If you consider this as a root, for example, then this value is bigger than this, and if you consider this left subtree, then this value is smaller than this. So this left and right subtree property is applicable at each and every level, at each and every node. For example, I have just shown that with respect to 32, 25 is smaller, but 43 is larger because it is left, it is inserted on the left, and 43 is its right child. Okay. Similarly, with respect to 19, all the three values are greater than 19. Okay. So this is the unique property of binary search tree that enable us to do programming. Okay. So we will see what all operations are possible on binary search trees, because through this property that on the left side smaller values are inserted while on the right side bigger values are inserted, we are able to search a key, and then we can perform insertion and deletion and lot many other operations. So all these are operations. Okay, searching, insertion, deletion are the common operations of each and every data structure. Then we will find the mirror image, we will find the smallest node, we will find the largest node of the tree, then we will also write the algorithm to determine the height of binary search tree. So these all operations we are going to discuss. Okay, so at first, how to search a key in a binary search tree. So well, we know the property of binary search tree. Okay, so with the help of an example, we'll discuss this. For example, we want to search a value 20 in the following binary search tree. So we will start from the root, okay, and we notice that the value stored here is 41, and we want to search 20. Okay, so we know that 20 is smaller than 41. So where we should go? Obviously towards left, because all the values on left is smaller than root. So there is no benefit if we go towards right, because we know the property of binary search tree. So we will now traverse towards left child. So as soon as we traverse from 41 to 10 and we reach 10, then we found that okay, we need to find 20. So that means now there is no benefit to go towards left, we should go towards right. Okay, so then from 10 to we will traverse to 25. Okay, now here we know 20 is smaller than 25, so we should go towards left, and here we find the value. Okay, so this is how searching takes place. Let us see through an algorithm. So this is the algorithm for searching in a binary search tree. So there is a possibility that if root is null, means tree is empty, then we will return null, and then we will print empty tree, and we may exit. Okay, then another case, else if this is not true, root is not null, then there may be possibility that root info, means whatever info is stored in root, that is equal to value, means we find the value within root only, then we will return the root. Else what is possible, that value is smaller than whatever is stored in the node. Okay, then we should call this function recursively for left child. Okay, because we know the value smaller than the node value must be stored towards left. Okay, otherwise if value is greater than the info stored in the node, then we will call this function recursively for the right child of the node. Okay, So we are doing recursion here instead of looping, okay, and we are taking decision whether we should go towards left or go towards right, depending whether value is smaller than the node info or the greater than, okay. So if we have traversed the whole tree and if we are not able to find the value, then we'll print value not found, and then this is a kind of error message and exit, okay. So this is the algorithm for searching a node. So after then we will now discuss insertion, okay. So let us first see example. So for example, we want to insert a new value with new node with value 7, okay, in this tree. So again we will first search the correct place. So first we will traverse to root node. We find that 7 is smaller than 41, so first we will go towards left. So when we go towards left, we will reach 10, okay, as shown in this diagram, and then we compare value 7 with 10, okay. 7 is smaller than 10, then again we will go towards left, okay, then we will reach 3. After 10 we will reach 3, okay, as shown here, and at 3 we find that 7 is more than 3, so there is no node towards its right. Then we will allocate the memory and insert that node in the right child of 3, okay. So this is how insertion takes place. It's quite easy. So let us see through algorithm, okay. So if we start, if root is null, means there is no tree is empty, then we just need to allocate the memory. We need to put the value whatever is being given by the user into that tree, that in the info part of the node, okay, and then we will set left child and right child both equal to null, because you know, whether this is the first node or whether this is the insertion later on, so it doesn't have any further child as of now, so that's why we need to set both L child and R child equals to null. Otherwise then this code is similar to searching, that if value is smaller than root info, then we will call this function recursively towards left child, otherwise towards the right child. So once we reach the null, okay, then we will insert the key like this, okay. So this is how insertion takes place. Fine. Now next important case is of deletion. So when we want to delete a node from a binary search tree, then 3 cases are possible. First case is that we want to delete a node that is having no children. For example, if you wish to delete any of the leaf node like 6, 37, 61, they don't have any child, so it's the easiest most, okay. Then another case is that we wish to delete a node having one child. For example, if you wish to delete 10, it is having one child, so that is one more case. And another last case is that if we wish to delete a node having 2 child, because it's a binary search tree, we can't have more than 2. There are total 3 possibilities. We might be asked by user to delete a node having no child, or to delete a node having one child like 10, or to delete a node having 2 child, okay. So similarly for 24, the same case would be applicable as of 42, because it is also having 2 child. So we will consider these 3 cases one by one. So first of all, we will consider the case deletion of a node having no children, okay. So let us assume that we want to delete a key 61 node with value 61, okay. So first we have to search it through the binary search tree. First we compare 61 with 24. We found that 61 is larger, so we will go towards right, then we reach 42, okay. Then we found, okay, 61 is still bigger than 42, then again we will go towards right following binary search tree property. Finally we reach that node, okay. Now it's very simple, we just need to create, free function as we have discussed in linked list, okay. So free function will be called, and for example, if we are using ptr pointer, then we will just write free ptr and this memory would be free, okay. Like this we have to do. However, we need to set null within the R child of previous node, okay. That we will see while doing coding, okay. Then we have to delete a node having one child. For example, we wish to delete a node with value 10 in the following example. We wish to delete node with value 10. So now 10 is not the leaf node, it is having one child, okay. So how to do that? It's very simple. We will first search through the binary search tree, and then as soon as we realize, okay, now the node is not leaf node, it's not terminal node, so then we will simply we will simply overwrite the child value within this node, and then we will delete the child node. Okay, so for example, we have searched through 10 for 10 in the BST. So we find 10 is less than 24, we will go towards left. As soon as we reach here, then what we are going to do, we will overwrite the value of child, only child, in this node. Okay, so 6 has come here. So you know one node can hold only one value. So 6 will overwrite 10. Then we will be having two 6 nodes. So then again we will delete this node which is not having any child, and it's simple like earlier we discussed. Okay, so this is how we delete a node having one child. Now the most important one is deleting a node having two children. So in order to delete a node having two children, then again we will replace the value of node with any of its child value. However, we need to determine the suitable value so that BST property should not be violated. You know, BST property that on left there should be smaller values, on right there should be larger values. So in order to do that, we should know there is some concept of called in order predecessor. Actually, there are three types of traversals which we will discuss in next video, that is pre-order, in order, and post order. Okay, so there I will discuss the complete concept. However, for the time being, I am just going to tell that in order predecessor of a node means the largest value in the left subtree of that node. Okay, for example, for 24, in order predecessor is 10. It's the largest value in its left subtree. Okay, similarly, in order successor means the smallest value in the right subtree. In order successor means for a particular node, in order successor means, for example, for 24, in order successor means the smallest value in the right subtree, that means 37. Okay, so this just we need to keep in our mind that okay, whenever we are going to delete such node, we will replace it with by either of its in order predecessor or by in order successor. Okay, so let us first learn how to delete a node with two children. For example, we wish to delete 42. Okay, so we will first search through 42. When 42 is more than 24, we will go towards right. Okay, after reaching 42, then we realized okay, both of its left child and right child are present. Then, for example, we are going to determine in order predecessor. In order predecessor means largest value in its left subtree. So in left subtree we are only having 37, so we will simply replace it. 37 would be overwritten here, and then we will delete 37. So like this we can delete such node. Okay, so in the next video we will discuss the complete algorithm of delete operation. So that's it for today. Thanks for watching.